Welcome to the afternoon session of Interpreting Conventional Plays in Unconventional Ways. As you all know, about 80% of all the wells drilled in North America currently are the unconventional horizontal type, which leaves 20% of the conventional still there, which is not an insignificant number of wells. So I'm going to be taking you through an unconventional workflow that will combine the disciplines of geology, petrophysics, sequence stratigraphy, geophysics, geomodeling, and give you the most comprehensive interpretation possible using some of the new capabilities in GeoGraphix, including fast seismic interpretation and our new 64-bit size vision. I will also introduce our new depth conversion and velocity manager in size vision, and take the depth converted seismic surfaces and integrate them into our geological modeling. At the end of the session, Justine will wrap it up with a question and answer session and other information for you. The GeoGraphix 2014 release builds upon our previous strengths in GeoGraphix, including a lightweight, easy-to-use capabilities. As a matter of fact, I'm doing all this on a laptop today. We optimize key unconventional workflows with innovative content. We're also moving into the engineering and G&G workflow integration, including advanced field planning with our new field planning module that allows you to develop field plans on planned surfaces well ahead of the drill bit. As a matter of fact, Scott Elfka, my colleague, will be demonstrating this in a later webinar, the new field planning capabilities. This has a tangible reduction in time and cost at an unparalleled price point in our market. Our traditional areas of integration have always been geology and geophysics. However, we're taking those disciplines and integrating them with full field planning that I spoke about earlier, that Scott will give a webinar later in December. We're also advancing our 3D visualization environment with a new tool to reveal all the 3D objects within a selected area on your map, which would include wells, surfaces, cross-sections, which would be revealed in a 3D environment where the cross-section would become fence diagrams complete with attribute backup, full lithology fill, and geophysical rendering. So on with our demonstration. The workflow I'll be evaluating is the Bakken up in Saskatchewan. Now this is a little different than the Bakken up in the Williston Basin. These are vertical wells that are drilling into well-developed sandstone reservoirs. So first we'll examine the structure and the distribution of the producing wells. Then we'll model the sand and pay intervals in PRISM and view the pay trend over the field to see if we can come up with some determination for why the fields are producing where they are. I will conduct a sequence stratigraphic interpretation in Smart Section, our geomodeling application, and then view the Smart Section cross-section with our depth-converted seismic backdrop being fed from size vision. From there, we'll jump over into the geophysical domain in our new 64-bit size vision. We'll view the key seismic horizons, generate seismic attributes, and then use our new velocity modeling and depth conversion tool to convert those time surfaces to depth. I will then take those depth-converted seismic surfaces and the attributes we develop in size vision and show them in the geomodeling tool Smart Section. I'll also insert the seismic depth-converted surfaces into the geomodel and combine them with well picks to give us a much improved geomodel with the updated seismic backdrop being fed from the new updated velocity model coming from size vision. We'll then view the subcrop thickness map and then develop an explanation for why the production is where it is and where we may extend the field in other areas. So with that, we'll jump over and begin our demonstration. We're going to start off in Smart Section. Smart Section is GeoGraphix 3D geomodeling application. Now in the past, our workflows have always been optimized to work to and from the mapping environment. GeoGraphix has always been very map-centric. Well, we've taken that paradigm one dimension further into the 3D geomodeling realm and have our workflows optimized from the geomodel. You're currently looking at the map view inside of Smart Section. I am mapping this detrital surface, which is the top of the Bakken in this area, using triangulation with minimum curvature smoothing. This surface is being modeled dynamically on the fly as I toggle that surface on and off using well controls from these wells in black. Now you'll also notice that we have a west to east plunging structure on top of the Bakken. However, it does not seem to close off to the west, so there seems to be something else that is influencing the structure and the production distribution of these wells in the area. So let's open this cross section right here, going from the northeast to the southwest. And let's zoom into the thicker wells in the center. Now, in addition to showing this in well-to-well cross-section, I'm also showing a Archie water saturation interpretation model that I built in Prism to show water saturation, and in addition to the model, I've modeled the thickness of the sand packages and the pay segments. So let's take a look at those in Prism. Down here, here's the Bakken package. And the model I'm using is basically an Archie interpretation where I've also generated a pay flag based upon the effective porosity being greater than 10%, water saturation being less than 50%, and V shale being less than 40%. That is modeled as the pay intervals in green here. The sand intervals are modeled where anywhere within the Bakken where I have V shale less than 40%, indicated by this yellow stippled pattern. Now I can take these two curve attributes and extract them using curve data statistics and then map them back in the Smart Section map environment. So I'll turn off the detrital surface and show my pay trends modeled from Prism. And I notice that I have a thick trend here of good porosity and low water saturation from the northeast to the southwest. So there seems to be some kind of stratigraphic control additional to the structural control controlling the distribution of these wells. Now let's look at a sequence stratigraphic interpretation here. And I'm going to change from my equally spaced well-to-well cross-section to a proportionally spaced cross-section. Now each of these surfaces is being modeled independently with triangulation and minimum curvature smoothing. Notice this red surface, there's the top of the detrital surface, that's the unconformity surface capping the top of the Bakken. The subcrop surfaces, as you notice here, are cutting right across the unconformity surface. That's because these surfaces are being modeled individually and naively. Now behind Smart Section we have a very robust 3D topology engine called Frame Builder. I'm loading all these different surfaces into the Frame Builder GeoModel from Wellbase, and I can assign constraint relationships between the surfaces. In other words, this Bakken sand, represented by the green line here, is going to control the conformance of the other surfaces from bottom to top up against that detrital unconformity. So the hierarchy of conformance will be the Bakken sand to the Bakken top sand to this unconformity unit to sub-Madison, Madison. So we're going to apply conformance upward against this unconformity. I'm going to apply the conformance tool, which will maintain thicknesses between the surfaces, and then the unconformity trimming tool, which then trims off the subcrop surfaces against the detrital. Now I do have a naively modeled velocity model from SeisVision that I can use as a backdrop. And at first blush it looks like it fits fairly well, except if you look at the detrital surface here, you see over in this area that it departs from the detrital events coming from the depth converted seismic backdrop. So let's shift over to SeisVision 64 and look at our analysis here. This section on the map is the same detrital surface in time, this surface right here, this blue surface, as I have identified and modeled using the well editor in log-m to identify my events in seismic against my geology. Also notice that we have a thickening between this unit here and the detrital and a tuning effect from the Bakken sand. We will extract those attributes using our attribute calculator, where we can extract 22 different phase, frequency, or amplitude attributes in addition to curvature attributes. I can take that surface and then take my peak amplitude based upon the event here in the Bakken sand, again indicating a northeast to southwest trending seismic attribute associated with this Bakken sand buildup. And also, I can put on there the contours for the isochron between the detrital and the torque wave, between this unit and this unit down here, indicating a thickening. So I have a seismic indication that I have good, thick sand being developed over the top of this structure. Now let's go back and look at let's go and get the time surface for the detrital back on there. And let's look at our velocity model here. Now you'll notice that a few of the depth-converted formation tops are not tying their seismic horizon counterpart here, particularly in this well here. That is because we have a poorly or naively modeled velocity model. So I'm going to use our new depth conversion tool to create a new velocity model between my 3D AutoPic torqueway surface, the Madison zero crossing surface, and the top detrital surface from the time horizons being associated with the formation picks coming out of well base. Now I'm going to apply all these for all wells throughout the volume using Velocity Manager to pick the velocity model that I built. Apply that, and notice now all the events are tying to their depth converted formation picks from well base. This has updated our velocity model. Now we can build a much more robust velocity field using these wells. These are the time depth pairs or velocity data coming from the velocity volume. And let's go ahead and grid those and then use that velocity field to convert to depth. Now we have a depth converted seismic surface that we can now insert into our geomodel in addition to a better 3D velocity model to use in our seismic backdrop back in Smart Section. So I'm going to turn off my petrophysical surface, go back to my detrital surface, and let's look at our cross section here. And I'm going to go back to my geosurface model property dialog, which interacts with the frame builder model. And for that detrital unconformity surface, in addition to data coming from well base, I'm going to take my ISOmap depth converted seismic surface for that detrital surface and insert that into my 3D geomodel. This will then be incorporated in the hierarchy of the conformance and then cascade throughout the whole model, and also update my depth converted seismic backdrop with the new velocity model. And notice the red detrital surface follows spot on its corresponding horizon event in the seismic backdrop. Additionally, we can look at our map and see now we have much more control because we're combining the well control with the seismic control from the depth converted surfaces from SeisVision, and see we have some indication of closure off to the west here. In addition to that, I can also map the detrital to Madison unconformity thickening from our sequence stratigraphic interpretation, and notice I have a thickening to the southwest. So let's combine both the detrital surface, and I'm going to go ahead and remove the color fill so it's a little easier to see, and use our new transparency on our color fill so we can see the structural contours underneath our thickening detrital to Madison isochore map. And now we can notice that we have an indication of a structural closure to the west, a northeast to southwest thickening of our major Bakken units, in addition to those other petrophysical and geophysical attributes, indicating that we probably have a good chance of putting at least two more good wells to the west of these two and extending the field in that area. So we've done a comprehensive interpretation combining geology, petrophysics, sequence stratigraphy, geomodeling, and geophysics to give us the most comprehensive interpretation possible. So with that, we'll return to our PowerPoint. And I think you can agree that this seamless workflow provides us a synergy that's really unparalleled, bringing all those disciplines together in a geomodeling workflow. I've introduced the new depth conversion and velocity manager and our new 64-bit size vision to give us the most comprehensive and highly integrated geoscience interpretation system on today's upstream market.